Good afternoon. My name is Rachel Webster, and I'm speaking today on quasar emission regions. I'd like to acknowledge some of the collaborators that I've worked with on this work: Suki Young from CSIRO, Chris Wolf and Chris Onken from ANU, and Matt O'Dowd from CUNY in New York. I want to start by showing a basic image of the emission regions around quasars. So we believe that the supermassive black hole at the center of the quasar is fed by an accretion disk. This is usually depicted as a stable structure and with various attributes, which I won't discuss today. And that provides an axisymmetric geometry to the quasar. The region perpendicular to the disk is occupied by what we usually call a disk wind. And you can see from this diagram that most recent thinking shows a slower outflow near the disk, fast with increasing velocity as one moves to the perpendicular region, where there may, in some cases, be a radio jet. So I'm going to be discussing this basic image a little bit more as we go along. So there are probably three key science questions that we want to address with regard to quasars. The first of all, we want to understand how they came into being. We see very high redshift quasars with apparently supermassive, very supermassive black holes at early times in the universe. How are the seeds of these black holes formed? And then how does the mass of the black hole grow over time and evolve? The second question relates to quasar outflows. What is the mass transferred by the outflow and its velocity and its composition, and how does that outflow impact on the host galaxy that the quasar resides in? We see relationships between the mass of the galaxy on scales many orders of magnitude larger than the mass of the black hole. And so apparently there is some relationship between the evolution of these two objects. And then finally, and perhaps most interestingly in some way, can we use quasars as standard candles to actually map out the structure of the universe? In order to do this, the quasars would need to be standard candles. In other words, we would need to understand the emission from the quasars and how to interpret that in a standard way. So a brief outline for this talk. I'm going to be concentrating on the ultraviolet and optical emission regions of the quasar. We usually call this the broad emission line region. And I will look at four techniques to interpret and understand those emission regions: reverberation mapping, broad absorption lines, caustic crossings, and finally just mention briefly some of the machine learning techniques that are now being investigated. I'll talk a little about consistency with other wavelengths, not at great length, talk a bit about modeling the disk wind, and finally I'm going to discuss these in order of their maturity at this point in time. So let's start with reverberation mapping. This is clearly the most mature of the techniques that I'll be talking about. And the way, or the very simple outline of how this works is that the quasar emits continuum emission from very near to the supermassive black hole. This continuum emission varies with time. The source of that variation is not important for this technique. And then the change in flux is transmitted and impacts on the clouds in the broad emission line region, which respond to that change in flux with a change in line emission. And if we then correlate the line flux with the continuum flux, we can get a time delay which can be interpreted as a light travel time. This then gives the radius of the emitting region and allows us to map out the broad emission line region. And so this diagram here shows, shows that time delay shown by this orange arrow here, and the cartoon here shows how the line flux might respond if the emitting clouds were in a thick shell at some fixed radius. And so the line flux is constant. There's an inner radius and an outer radius to the shell, and you can see how the line flux might change. For example, if the emission was turned off. So how then is this interpreted? Well, usually a very simple virial formulation is used, and you can see the equation here. The mass of the black hole is related to the velocity squared multiplied by the radius divided by g. And so if you can measure the line width, which will give you the velocity, and the radius, which we get from the time delay, then we can measure the mass of the black hole. Now, in order to do this, there's an unknown factor, F, which is included to incorporate all the variables that we don't understand about this process. It's usually taken to be 1 in most measurements of black hole mass. And I'll say a little bit more about the value of F as we go along. But from these very simple, well, the measurements are not simple in that they take considerable lengths of time, tens of years, but the analysis is reasonably straightforward. But what we see is that the higher ionization regions are closer to the black hole, and in other words, they have shorter time delays. And then in order to understand some of the more complex aspects of the emission regions, most of the interpretation is based on this very simple model of the emission region with what I would term phenomenological corrections. Now, into that value of F are some quite significant complexities. And so, for example, the angle of viewing, the direction that we're actually seeing this axisymmetric sector from is not included. There's a transfer function, once the change in continuum emission interacts with the emitting regions. And of course, there may be different geometries for the individual emission lines. And so one of the questions that we might ask is whether or not a more nuanced model of the broad emission line region is required. I'm going to move now to the second of the techniques, and this is the one that I have been thinking quite a lot about, which are what broad absorption lines can tell us about the geometry of this emission region. So in this diagram here, we see a standard model, a standard spectrum of a quasar. So this is an average quasar spectrum from the Sloan Digital Sky Survey. And you can see the Lyman alpha lines, the carbon-4 lines, the carbon-3 lines, and so on. In a broad absorption line quasar, what we see are some very deep and broad emission line, absorption line troughs, just blueward of the emission line. So you can see there's a carbon-4 absorption line here and a silicon-4 absorption line just blueward of the silicon-4 emission line. And there's a little bit of absorption, in this case from blueward of the carbon-3 as well. And the lower example here shows that in some cases, these BAL quasars are indeed very reddened, which is not surprising if indeed we're seeing the quasar through an absorbing column. So the question is, where do these broad absorption clouds lie, and what can we what can we use these to tell us something about the wind that we expect to be emanating from the quasar? Uh, these absorption troughs have variable offsets from the emission lines, um, and they're sometimes 20,000 kilometres a second wide, so really quite broad. We usually define the broad absorption troughs. Well, in all cases, we seek the high emission lines, so that's carbon 4 and silicon 4, but sometimes we also see broad absorption troughs from lower emission lines, such as magnesium 2 and iron, but in those much rarer events. And so the question, so um, can we use these to untangle geometry? So the simple interpretation is that the broad absorption line of sight intersects a dense part of a wind. And so early models suggested, so here's one from Elvis, suggested that we had a narrow wind, and that when we viewed the quasar, we're basically looking down the broad absorption or down the disk wind, and that gives us a broad absorption line. And if we're looking from some other direction, we're not looking down the wind, and therefore we don't see the absorption trough. And there was also the early model from Norm Murray that had the wind basically skirting the accretion disk. And again, we're seeing the broad absorption line quasar through that denser column of gas. So the work that I've been doing with Suki Yong started from a slightly different direction, where we looked at a very simple model of the wind, which was based on a stellar wind model from Schlossman and Vitello, and this basically modeled the wind with a rotational and a poloidal wind component. So the rotational component was due to the rotation of the accretion disk, transferred to whatever appropriate radius. And then there was some outward flowing component, usually the physics of which wasn't defined, but usually modeled in as a fairly simple power law. What we did was look at different regions of that wind, and it's shown in this little cartoon here, and look to see what the shape of the observed emission line would be if the gas was in one of these regions. And these plots on the right-hand side here show the different line shapes in the different regions as they're outlined in the diagram here. And what you can see is that the line shape and the line offset from where you would expect it to be varies with the position on the diagram. So in other words, if we're looking down in this corner here, we basically don't see any outflowing wind, but we see different shapes as we go out along this axis, which is not surprising. But once we go up into this top corner here, we see the outflowing component of the wind. So the velocity is blue shifted. And again, we get different shapes depending on exactly where we are. So the basic idea is that the line shape and offset are a function of position of wind viewing angle. We use this to estimate how this would change the black hole mass depending on the angle of viewing. And you can see here the inclination angle starting from pole on round to edge on varies by a significant amount depending on the direction of viewing, if you take account of of these different zones, and that uncertainty was a factor, a multiplicative factor of 10 both ways. So that would mean then that this F factor in front of our equation could be quite significant. A second result that we found was when we looked, first of all, we thought that that started to suggest that the line width, the velocity offset of the line, and the asymmetry of the line were all important in understanding the structure of the wind, and that perhaps the direction that we're viewing from might change these values. This is a plot of the difference in velocity position of carbon-4 and magnesium-2. So carbon-4 is a high ionization line, magnesium-2 is a low ionization line. And what this is telling you is that instead of those two lines sitting where we would expect them to sit, the carbon-4 line is usually blueward of that position by up to a few thousand kilometers a second. Interestingly, when you correlated that offset with the ratio of the line widths, we see quite a strong correlation. And so this is the carbon-4 ratio over the magnesium-2 ratio. And if you take this correlation at face value, what it suggests is that when we're in this part of the diagram, we're looking edge on at the, at the emission region. And when we're in this part of the diagram, we're looking face on. And we did some further analysis that at least provided consistency with this interpretation. And so, so what this suggested then is that the carbon-4 line is moving towards us, so it's in that upper part of the wind, whereas the magnesium-2 was in the lower part of the wind, and so had a larger colloidal, a larger rotational component and a smaller colloidal component. Very strongly, this suggests, and you know, there is no other way of interpreting this, that the carbon-4 and the magnesium-2 are emitted in different parts of the winds. So what did we learn from this? We suggest that the angle of viewing does matter in interpretation of these emission line characteristics, and that BALs, and I haven't shown the statistics here, but when we looked at the statistics of those emission lines, it suggested that the BAL quasars are viewed from exactly the same range of viewing angles as the non-BALs. And so this idea that we had a narrow wind that was responsible for the BAL did not hold up. And so we suggest that instead we're looking at randomly located regions of high density, which are responsible for the BAL structure. The carbon-4 absorption is, as I mentioned earlier, closer to the pole, and the magnesium-2 absorption is closer down to the disk with a higher rotational component. When we looked at the magnesium-2 BALs and the Fe low BALs, the ones that also showed Fe absorption, that showed some directional dependence. And so we believe that those viewing of those particular BALs may be close down to the disk. It's very unclear what the colloidal component, the physics driving the colloidal component is, but it's unlikely to be the same as the stellar wind models. So the next question was, well, we also see absorption lines in the X-ray, and I don't really have time to go through that in detail, but the X-ray absorption is in some cases much more extreme than the UV absorption. Some have extremely high velocities, ultra fast outflows, but sometimes they have related UV absorption and sometimes they don't. So again, suggesting that the X-ray and the UV absorption are not happening in the same parts of the wind. And so when viewed from different directions, they don't always align. The X-ray observations also show what we call warm absorbers, and those are at much lower velocities. And these have some blue asymmetries and clumpy structure. So we're starting to get a picture of quite diverse emitting regions and absorbing regions in our outflow. So the next technique that can be used to image this disk wind is caustic crossings. And the basic idea here is that we have a multiply imaged quasar. So essentially we're seeing a quasar from 2 or 4 different directions, ideally 4 different directions. And then as those quasar images, the different quasar images move across the caustic network created by the stars in the macro imaging galaxy, different parts of the quasar are magnified by different amounts. Okay, and if we can see these changes, then we can actually disentangle the gravitational lensing and measure the size scales of those emitting regions. Since the emitting regions are typically on scales of micro-arc seconds, this is really the only technique that will allow direct imaging of the emission regions, both the continuum region and the broad emission line regions. So this diagram here shows it's a cartoon of the emitting regions of the quasar, but simply meant to illustrate how this works. So you can see different colored regions just in a disk. And these are moving across a caustic pattern created by the stars in the lensing galaxy. And the light curves that you will see for the different colors are shown in the second plot here. So you can see that the smallest regions are magnified by the greatest amounts, which is what you would expect. The larger regions, the magnification is washed out. And then if you sample these light curves with something like the LSST from the Vera Rubin Observatory, then you can see that you can actually determine the relative sizes of these emitting regions. So how do we, is this technique going to work, basically? Well, so the first thing is that chromatic, we call this chromatic microlensing or differential microlensing, where regions of different sizes are magnified by different amounts. And this has definitely been observed, both for the continuum region. And so there's an example from a paper here by Nick Bate. And this was used, so these were multicolor observations of a quasar, and used to try and measure the profile of the continuum emitting region. And you can see that in fact it gives some indication of the temperature profile of the continuum. And our best estimate from this work was that it was not consistent with a Sunyaev disk, which is of course a very important result. The second example I've shown here is some particularly fabulous spectra from Gemini, and in the bottom plot are simple ratios of the 4 different images. But what you can see is that at the location of the emission lines, there are differences, which tells us that there's differential magnification of the emission regions. The second example is from a paper that hasn't been widely appreciated, but showing differential microlensing of the emission regions. So it's showing resolution across the emission regions. And the blue lines show the microlens regions. So these have been broken into microlensed and non-microlensed emission, and it shows quite clearly that the H alpha and carbon-4 microlensing is different, suggesting that the carbon-4 emission region is outflowing and the H alpha emission is in a Keplerian disk, which is consistent with other information that we have. So the learnings that we have from this is that if we can get clean caustic crossings, time resolved, light curves of the emission regions, then we'll be able to trigger spectroscopic observations, which will enable us to measure the sizes of the emission regions, which will be enormously advantageous in actually measuring the geometry of these regions. The large, synoptic survey telescope will be able to do this. Although the interpretation is complex, the microlensing signature is unambiguous, and if we can get that image of the emission region, then we should be able to model it in detail. And this is quite complementary to the reverberation mapping and BAL experiments. So just briefly, I want to mention that people have now started to use machine learning techniques to measure both photometric redshifts quite successfully, as you can see here on the left, and then to use those photometric redshifts to measure black hole masses. Now, of course, this relies on having a model of truth, and I hope I've indicated that that is so far still being evolved. Okay, so if we can predict, if we can understand those emission regions, then we will be able to measure black hole masses and redshifts for a lot of quasars. Now, I just briefly want to mention the state of modeling at this point in time. Daniel Proger has been measuring or has been modeling radiatively driven winds, and the things that I want you to take away from this is that the winds are variable and changing with time, and it looks very much like the sort of emission that we see from the sun. So in other words, you know, we've got these streams of dense emission flowing out from the inner parts of the AGN. And you can see that shown in this density plot here on the right. Another attempt at modeling comes from Andrew King, who has done some theoretical modeling of momentum-driven winds. So this is now with accretion coming in and then being driven out. And basically, these Eddington accretion episodes must produce outflows, and they must have high velocities, significant and high velocities. And they may persist long after the AGN actually flares optically. In other words, the emission from the AGN actually flares. And then finally, the third type of model is a magneto-hydrodynamically driven wind, and these will always produce high velocity outflows, which may or may not have both X-ray and UV absorption features. And what I would like to suggest is that it is likely that all three of these mechanisms might be important in understanding how our disk winds actually behave. My final comment is just about, you know, are we missing something when we actually look at these outflows? We assume a static direction for the inflow. We assume that it's smooth, but perhaps it's lumpy. And indeed, if we look at the Milky Way, we see that the inner region has random orbits. And so it's possible that the accretion is happening from a range of different directions. And if we look at extreme tidal disruption events, we see that the behavior is very dependent on the axis, the rotational axis of the black hole and the direction that the accretion is coming from. And some recent simulations have shown that indeed that those black hole interactions can produce huge outflows, as we might expect. These are my concluding remarks, and I think perhaps the key point I want to make is that these outflows may be quite the outflows may be quite dynamical rather than stationary, and that the accretion inflows may also not be the simple accretion disks that we sometimes assume. Thank you.